Hello guys, this is section 6.4, states of matter and changes of state. Sometimes instead of changes of state, we use changes of phase or phase change. However, that's the same thing. It's about changing the physical state of the matter from solid to liquid through melting process, or from liquid to solid through a freezing process, from liquid to gas through evaporation process, and from gas to liquid through condensation process, and from gas to solid, directly to solid through deposition, and from solid to gas through sublimation. However, we're going to ignore this and we're going to focus more in a natural way, in a more common way of the phase change through solid to liquid and vice versa, and from liquid to gas and vice versa. All forms of matter can exist in three different physical states or phases, which are solid, liquid, and gas. In solid, strong forces of attraction or bonds hold these particles in a fixed position. They still vibrate, but they cannot easily slide past each other or move from one place to another. In liquid, particles have more kinetic energy than particles in solid. This causes the liquid particles to vibrate and slide past each other and move from one place to another. They are free to move, but they are still together. This gives the liquid the ability to flow and pour, and ability to take the shape of the container. In a gas, particles have much more kinetic energy than particles of liquids, and even much more than particles of solids. The particles of gas vibrate more vigorously than particles of solid and liquids, and they move large distances past to each other. This gives gases ability to flow and to fill containers like cylinders of gas, and expandable containers like balloons and tires with a great pressure. So we're going to talk about change of state of matter. When solid, liquids, and gases absorb or release enough thermal energy, they may change the physical state, as we call it, as a phase change. So if they absorb thermal energy, solid can become a liquid, and liquid can become a gas. And if they release thermal energy enough, gas can become a liquid, and liquid can become solid. Let's focus for a moment at a change of state of water. As ice, as a solid water, absorb thermal energy, its particles begin to vibrate rapidly. The kinetic energy of the particles will increase. Temperature will increase as well. As particles absorb more thermal energy, forces of attraction are not strong enough to hold those particles in a fixed position, in a structured way. So that means solid reaches its melting point, where the particles begin to slide past each other and move from one place to another, but they are still together. At this point, the solid begins to change into a liquid. This change of state is called melting or fusion. We can do an experiment like this. We have a container with ice at a temperature, for example, minus 10 degrees Celsius, and we heat it up. As thermal energy continues to be absorbed during the melting process, we can notice that temperature does not change. It remains 0 degrees Celsius until the last ice crystal has melted into liquid water. So the temperature is going to be 0 degree as the last piece of ice is going to melt into water. As a liquid water is formed and will continue to absorb thermal energy, its particles will move faster and faster and kinetic energy of those particles will increase, so the temperature will increase. As the speed of the particles increase, the force of attraction becomes weaker and weaker, and it becomes more difficult for particles to stay together. Eventually, the liquid reaches its boiling point. So at boiling point, the liquid water changes into a gas called water vapor. This change in state is called evaporation, or simply evaporation. The thermal energy continues to be absorbed during the boiling process. But interesting thing is the temperature will not increase. So all the thermal energy goes toward changing the phase of the water from water to water vapor. So that means that the temperature will remain at 100 degrees Celsius until the last drop of water has changed into a gas state, which is a water vapor. The molecular theory describes how energy can be added to a system without increasing the temperature of the system during the phase change. Now let's look at the diagram. It is in a Kelvin. It starts at a minus 30 degrees Celsius or 243 Kelvin. As energy is absorbed, kinetic energy of the ice will increase, so those particles will move more rapidly. As the 0 degrees Celsius or 273 Kelvin reached, then all amount of energy that is absorbed goes toward change of structure of the ice, and ice will start melting into and changing into water. At this phase, we have a mixture between ice and water, and the amount of thermal energy that is absorbed will go toward potential energy, not kinetic energy. Potential energy of the changing the structure of the ice until a last piece of ice is melted. Then as everything is changed into water, then amount of thermal energy that is absorbed thereafter is going to go toward increasing the kinetic energy. An increase of the kinetic energy will increase the temperature until the temperature will reach 100 degree or 373 Kelvin. Then again, the same thing happens. Amount of thermal energy that is absorbed goes directly to a potential energy to change the structure from liquid to make those particles to move free as gas or water vapor. As the last drop of water is evaporated, then amount of thermal energy at that point goes again toward kinetic energy, which will result into change in temperature. So temperature will increase after that point. Let's start with a heating graph. A heating graph is a graph that shows temperature changes that occur while thermal energy is absorbed by a substance. So we already talked about how it changed from ice to ice and liquid together when ice is melting. And then we have warming up the water. Then we have starting boiling the water. And we have liquid water and water vapor in this phase. And then after the last drop of water is boiled, then we have increasing the temperature or kinetic energy of the water vapor particles. You should be able to draw a simple heating graph like this one, when you have temperature on vertical axis and thermal energy absorbed on x-axis. So there are few critical temperature. It is a starting point. Starting point you can label as a T1. Then as thermal energy is absorbed, temperature will increase and it reaches to that phase change from solid to liquid. Then you can label that temperature that is constant as a temperature of fusion, or TF. Then when the phase is already changed from solid to liquid, then thermal energy that is absorbed goes toward kinetic energy, which is associated with a temperature change, temperature increase, until it reaches a point where another phase change happens between liquid to gas, and that temperature you label it as TV, as temperature of evaporation. And when completely gas is formed, so liquid is turned into gas, then thermal energy that is absorbed goes toward increase of kinetic energy, which is going to be shown as increase of temperature until it reaches a certain point that is temperature, lost temperature, or temperature 2. A cooling graph is a graph that shows the temperature change that occurs while thermal energy is being removed or released from a substance. So it starts from any point, but full graph will start from gas. So from gas, it starts and decreasing the temperature, so releasing the thermal energy into environment until it reaches the point at the condensation point, when a gas is starting to turn into a liquid. At the point when all molecules of gas are already turned into a liquid, then the thermal energy that is released goes toward decreasing the temperature until another phase change happens when the temperature goes toward 0 degree. When it reaches 0 degree, then the first piece of ice, crystal of ice, is formed. And now we have a process of changing the liquid to a solid, so the temperature will not change. So thermal energy that is released, it is taken from potential energy. Then at this point, when everything is already crystallized into ice, then if the energy is removed from system, is released to an environment, then ice will cool down from 0 to negative values. From this case, it is to -10. Again, you should be able to draw a simple cooling graph. What you are seeing on that simple cooling graph are the temperatures are reversed. So temperature T1 is where it starts cooling down, and temperature T2 is where it ends that process. So you see the two phase changes. Not all the graphs may have all phase changes, may have one, or may have both. However, depends on what you are being asked. You should be able to draw a full cooling graph like this, or partial cooling graph. Latent comes from a Latin word that means hidden. This is because of during the phase change, nothing is reflected in change in temperature. So you don't see any difference. Because that amount of thermal energy that is absorbed or released goes toward change of phase. That means that goes toward potential energy. The latent heat is a total thermal energy absorbed or released when a substance changes state, is measured in joule. The latent heat of fusion, it is the amount of thermal energy absorbed when a substance melts or amount of thermal energy released when it freezes. The latent heat of evaporation is the amount of thermal energy that is absorbed when a substance evaporates, and it is released when it condenses. The specific latent heat is the amount of thermal energy required for 1 kilogram of substance to change from one state into another, and is measured in a joule per kilogram. A specific latent heat of fusion, it is a thermal energy required for 1 kilogram of substance to melt or freeze, and again is measured in a joule per kilogram. So the specific latent heat of evaporation, it is a thermal energy required for 1 kilogram of substance to boil or condense, measured in joule per kilogram. Let's calculate the amount of thermal energy absorbed or released during the change of states or phase change. The latent heat of fusion is calculated using formula QF is equal mLF. That means M is mass of the substance and LF is specific latent heat of fusion. For latent heat of evaporation, we use a formula QV is equal to mLV. So M is mass, LV is specific latent heat of evaporation. And here is where you get those values from. Make sure you look at melting point and boiling point, and you're looking to a specific latent heat of fusion when it's melt or freezes, and the latent heat of evaporation when you're looking for boiling or condensation. Let's start with a simple problem with the thermal energy during the phase change. How much thermal energy is released by 652 grams of molten lead when it changes from liquid to solid? Here is what is given. Mass of the metal is lead this time is 0.652 kilogram. Specific latent heat of fusion is 2.5 times 10 to the power of 4 joule per kilogram. Where did you get this? From a table of data. Temperature for fusion is 327.5 degrees Celsius, and what is required is quantity of heat during the fusion. So here is a cooling down graph. We're looking for only when it turns from liquid to solid at a 327.5 degrees Celsius. So the formula is QF for a fusion is equal mass of the metal or a substance is lead this time times LF, specific latent heat of fusion. We have everything now to calculate what we need, the quantity of heat during the fusion. 0.652 kilogram times 2.5 times 10 to the power of 4 joule per kilogram. Kilogram with kilogram cancel. So what is left is negative 16,300 joule. Now where this negative came from? So there's no negative number here. Both of those are positive. You have to do it. You have to put it, the negative number there, because it is a releasing the thermal energy. And when it releases thermal energy, that is a negative value. Remember that during that phase change or state of changes of state, there is no positive or negative. It's always positive. You have to change the sign. In a release, there's a negative. In an absorb, is positive. Keep that in your mind. It's very important. Here's another practice problem, but this time it's a little bit more complex because it has to do with the two phases, warming up and phase change. Ethyl alcohol is a liquid at room temperature. How much thermal energy is absorbed when 135 grams of ethyl alcohol at 21.5 degrees Celsius is heated until all it boils and turns into a vapor? So what is given here is a mass of alcohol of 0.135 kilogram. That's a standard unit. Specific heat capacity is 2,460 joule per kilogram per degree Celsius. Specific latent heat of evaporation is 8.6 times 10 to the power of 5 joule per kilogram. Temperature that is given is 21.5 degrees Celsius. We start from that temperature and we end up to a temperature of evaporation that is 78.3 degrees Celsius. Where did we get this? There's no 78.3 degrees Celsius mentioned on a problem. You look at the table of data when you see that alcohol can evaporate at 78.3 degrees Celsius. So what is required here is a total amount of thermal energy that is absorbed. Now, we're looking at temperature T1 there, which is not as a traditional one when we have the full change from a solid to a solid and liquid to liquid and then liquid and gas and gas. What we're looking for is just starting from this T1 here, which is 21.5 degrees Celsius. Then we're going to start what is total amount of thermal energy that is absorbed. So what we're looking for is this section warming up, and that is Q1, which is MC delta T, and another section would be phase change. That will be turning into vapor, alcohol liquid into vapor. So that amount of heat, it is calculated by mass time specific latent heat of evaporation. Okay, so we have everything to calculate total heat, total amount of thermal energy that is absorbed. Now, Q1 is equal MC delta T. So mass is already given, 0.135 kilogram. C, it is already given, 2,460 joule per kilogram per degree Celsius. And change in temperature is from final 78.3 minus initial 21.5 degrees Celsius. So this one is the very crucial one because it tells you it is absorbed or released. So sign of the thermal energy is going to be determined by change in the temperature. However, you know already that is absorbed because it's already mentioned. So now we're looking at 18,863.28 joule. So that's a positive. Make sure you put that positive so you will not get confused in the future. Okay, the next step would be how to calculate that latent heat of evaporation. Use a formula. So mass is given, 0.135 kilogram, and specific latent heat of evaporation for alcohol is 8.6 times 10 to the power of 5 joule per kilogram, and kilogram cancel. What is left there is joule, and now remember that is a absorbed energy. It's positive. So it's a 116,100 joule. Now we're ready actually to add them up together, and the total is going to be positive, so plus 134,963 joule of energy. Now we have a practice problem that includes almost everything. 500 centimeter cube of ice at minus 10 degrees Celsius absorb thermal energy to reach temperature of 110 degrees Celsius. Draw and label temperature thermal energy graph. Now, before you draw this, It's about absorb. So it is a warming up graph. Okay? The second thing that you need to take into consideration is where those temperatures start. It starts from negative 10 degrees Celsius to a positive 110 degrees Celsius. Okay, another step that you have to think of is what is included on that change of temperature. There are freezing, or in this case is melting, and another temperature is that is included on that minus 10 degrees Celsius and 110 degrees Celsius is evaporation. So those four temperatures are critical, crucial to draw that graph. So with those four, you can draw exactly what we have seen before. So it's a minus 10, it's going to warm up to a 0 degree, it's going to start melting, and it's going to warm up as a liquid, and then it's going to start evaporating, and then it's going to warm up as a gas. So those are the one. Another thing is you have to label Q1, Q2, Q3, Q4, and Q5, because you're going to calculate those individual amount of thermal energy that are absorbed for each individual section. Section 1 when ice is warming up, and section 2 when ice is melting, section 3 when a liquid water is warming up, section 4 when a liquid water is boiling, and section 5 where the water vapor is warming up, is getting even hotter. For section B, how much thermal energy is absorbed for this change? You need to calculate the total amount of thermal energy on phase 1. That means warming up the ice, calculating Q1. In a phase change, Q2, when ice is melting. In a phase 3, when liquid water is warming up. On phase 4, which is a phase change of state from liquid to gas. And for Q5, when the gas is warming up or water vapor is warming up. So all those has to be calculated individually. So I want you to pause the video, get a pencil, pen, calculator, because you have to do that with me in order to understand and learn. So pause the video and do it. You can pause the video time after time to catch up, actually, but obviously you need to have something to write down and do it with me. Now, if you take a look, there's a lot of given data here. Not all of them are given at the problem. Some of them you have to extract from table of data for specific heat capacity table of data and from phase change table of data. So once you have those, then you can start. Volume is given, not mass, volume. Be careful here, because it's a 500 centimeter cube volume of ice, not water, ice. Temperature 1 is given where it starts from negative or minus 10 degrees Celsius. Specific heat capacity of ice, not water, ice, that's how we are starting with, is 2100 joule per kilogram per degree Celsius. Now from table of data, we know another thing, that ice is going to melt at 0 degrees Celsius. From a table of data, again, we have latent heat of specific latent heat of fusion for ice is 3.4 times 10 to the power of 5 joule per kilogram, or for water, it's the same. Now, specific heat capacity of water is different from ice, is 4,180 joule per kilogram per degree Celsius. Now, temperature of evaporation is 100 degrees Celsius for water, ice, steam. Temperature T2 is already given from the problem is 110 degrees Celsius, and latent heat, specific latent heat of evaporation, you get it from table of data, 2.3 times 10 to the power of 6 joule per kilogram. And the last one is specific heat capacity of steam. It is 2010 joule per kilogram per degree Celsius. That is taken from table of data. Remember that we are talking about volume, and a formula has a mass in it. So you have to look for density. Density of ice, not the water, ice, is 0.92 gram per centimeter cube. So what we're looking for is a total amount of thermal energy that is absorbed. So we have all of them adding together. So then, one more time, we have to just look at formulas to use for each individual section. Q1, which is warming up ice, is MC ice change in temperature from fusion minus what it started. It started from -10, -10. Phase 2 is a phase change or fusion. That is M specific latent heat of fusion. Phase 3, or warming up a water from 0 to 100. So from evaporation minus fusion. So 100 minus 0. Remember that here is a specific heat capacity of water, not ice anymore, water. And section 4 is a phase change, is evaporation. The formula is mass time specific latent heat of evaporation. And a phase 5 is warming up the steam or a water vapor is equal to mass time specific heat capacity of steam or water vapor, whatever you label it, it's up to you. And then is T2 minus, that is given, minus temperature of evaporation, which is 100 degrees Celsius in this case for water, but for other substances might be different. So be careful on those temperatures because you have to just look at the table of data. After we have all the data, we are ready to calculate total amount of thermal energy that is absorbed. But we need to calculate mass. Either a mass is given or we need to calculate it and convert it to a standard unit. So in this case, we have 500 centimeter cube of ice. Density of ice is 0.92 gram per centimeter cube. So centimeter cube and centimeter cube cancel. So what we have, mass is 460 gram. But we have to convert it to a standard unit, which make 0.46 kilogram. Then next, we can start to calculate amount of thermal energy that is absorbed during the warming up the ice to the fusion section. So MC delta T. So remember, it's a temperature final minus temperature initial. Many people make that mistake. They just reverse it, and most likely that number will become negative. So remember that when it's absorbed, that has to be positive. If you get with a negative number, you're doing something wrong. So that is something, a self-check for you. Okay, so after plugging those numbers in the formula and in your calculator, then we get 9,660 joule for phase 1, warming up the ice. Then the second phase would be a phase change. So state of solid will become liquid. The formula is MLF. So that's a specific latent heat of fusion, which we already got, 3.4 times 10 to the power of 5 joule per kilogram, and mass is the same. That's another mistake that people do. Mass never change. Never change. Okay? Volume change for a from ice to water to liquid, but mass never changed because mass is the amount of matter in it, how much stuff that substance has. So we have everything to calculate, and that will be a positive. Why? Because amount of energy is absorbed. Another tricky thing that you can keep that in your mind is that all the numbers for all phases, all sections that you calculate must be either all negative or all positive. Cannot be mixed. That's another thing. Self-check. Make sure you do that. All positive or all negative. Phase 3 or section 3. What is amount of thermal energy absorbed when the water that is formed already at a phase change is heating up until what? Evaporation temperature. So then make sure that the mass is the same, 0.46 kilogram. Now for specific heat capacity of water is different from ice. You see that there's a huge difference. And the temperature varies from 0 to 100. So final minus initial, 100 minus 0 degree. Then you can calculate it. You get 192,280 joule. We can continue with section 4 when there's another phase change from liquid to gas. So that is evaporation. So it's a latent heat of evaporation, which is mass times specific latent heat of evaporation. We have a mass, which is the same again. Then we have 2.3 times 10 to the power of 6 joule per kilogram. So kilogram and kilogram cancel. So what we have is 1,058,000 joule. And that is positive because it's absorbing the energy. And finally, the fifth section, which is warming up steam or water vapor. Make sure there is specific heat capacity of steam or water vapor, MC delta T. So change is final temperature minus initial temperature. The initial temperature for that phase is 100 degree. So 110 minus 100. And another thing is make sure this is specific heat capacity of water vapor or steam. Then we are ready to calculate the last one. It is 9,246 joule. And the last step would be just add them up. And as I said, all of them are positive. Has to be either a positive or all negative. In this case, we're talking about absorbed thermal energy. So all of them has to be all positive. If you happen to make a mistake and one of those actually happen to be negative, go back, check it. You made a mistake. Cannot be negative. Has to be all positive or all negative. There is no way that you have one of those thermal energies that you calculate to be a negative one. When we are talking about absorbed, is all positive. Anyway, so we are ready now to add them up, and it's a 1,425,586 joule of energy. If you remember in the Science 9, we talk about why water is a special substance. And one reason was chemistry related, chemical property related, which was water is a universal solvent, and other three are physics related. And we already talked why water absorbs a lot of heat, a lot of thermal energy when it warms up. Now we're going to focus on the water is the only substance that exists in three forms. in nature: solid, liquid, and gas. Now let's focus on density. Most solids sink in their respective liquids. For example, solid iron sink in a liquid iron. This occurs because the particles are packed together in a solid state than particles of the liquid, making the solid denser. However, water is different. Ice float on the water because water is one of the few substances whose solid is less dense than its liquid. So, density of water is less than density of ice. So density of liquid water, it is less than density of solid water, which is ice. How can we explain that solid water has a smaller density than liquid water? That can explain with the shape of the molecule. Water molecules are V-shaped. They have two hydrogen atoms attached to one oxygen atom. At a temperature above 4 degrees, water molecules are relatively disorganized and they move around. So that explains why the water liquid have ability to flow and to take the shape of the container. However, under this temperature, kinetic energy of the molecules is smaller, is starting to form a structure. So the molecules of ice take up more space because they are more organized and spaced out. Water damage is very expensive to repair in a household. The expansion of the water when it freezes can cause a lot of problems. Pipes in homes or underground can break under the pressure of the expanding frozen water. When the water flows out of the broken pipe, will cause a flooding or a damage. So you never leave the house in a situation when temperature inside of the house during the winter can drop under freezing point. And that's it for this lesson, and we'll continue the next one. Section 6.5, Heating and Cooling Systems. This is a short lesson. You're going to learn about some application of thermal energy. Let's start with a heating system that we are more familiar with. Conventional heating systems use either electricity or fossil fuel as a source of thermal energy. Electrical heating systems generate thermal energy by allowing electric current to pass through a metal wire that has a high resistance to the current that passed through them. In this way, energy transformation occurs, electrical to a thermal energy. As we have seen it before, it is a very high efficient energy transformation. Similar wires are used in elements of the electric stove and a toaster. Now, fossil fuel systems generate thermal energy by burning fossil fuels such as oil, coal, or natural gas. The thermal energy is transformed through a building by convection. Forced air heating system is most popular used. The forced air heating system uses a furnace to warm air to heat buildings and houses. In this system, the warm air passes through ducts that eventually reach vents located in the floor or ceiling. The warm air is transferred through a building by convection. As the warm air enters through a room through vents, colder air is pushed through another set of ducts called air returns, providing more air for a furnace to heat, and that process continues. Fresh air is also brought into the system through the intake pipe out of the building. This is a diagram how forced air system works to heat the house. So air, as it is heated by a furnace, it is supplied through a vent throughout the house, and the air is returned to reheated through a furnace through returns pipes. Hot water heating system is another heating system used. A hot water heating system uses a boiler to heat water in order to heat buildings. The boiler uses electricity or burn fossil fuel to heat the water in the same way as in a forced air heating system heating air. A hot water is pumped through pipes that reaches the radiators located in the various rooms of the buildings. This system is efficient and quiet, but it is expensive to set up and sometimes expensive to repair, as the leaking the water may cause water damage. Conventional cooling systems include air conditioners, refrigerators, and freezers. The air conditioners, refrigerators, and freezers are very similar. They use evaporation of the liquid to absorb thermal energy from air. First, the compressor puts a special type of gas called refrigerant under pressure. Increase of the pressure will increase the temperature. The warm refrigerant gas runs through a coil of tubes where it starts to release some of thermal energy into the environment. This way, the refrigerant cools from gas into a liquid. The next step, the liquid then passes through an expansion valve, moving from high pressure area to a low pressure area. Decreasing of the pressure will decrease the temperature. So that's how it cools off what it is inside of the refrigerator or freezer. After expanding and decrease of the pressure is associated with a decrease in temperature, at this point, the liquid refrigerant absorbs thermal energy from surrounding air and evaporates back into a gas. The surrounding air cools down as a result and the temperature drops. The compressor of the air conditioner gets very warm, so air conditioning units are installed outside of the building where the thermal energy can be released into external environment. A refrigerator or a freezer use the same type of compressor and a coil system as in air conditioner, but here is all in one unit. The only difference is that the cooled air produced is kept inside and the warm air is released in the external environment outside of the refrigerator, usually at the back of the refrigerator, but still inside of the room. That's why refrigerators and freezers warm up the room where they operate. Heating and cooling system contain a thermostat to sense the temperature of environment and turn the furnace or air conditioner on and off accordingly. Conventional thermostat contain a coiled bimetallic strip and a mercury switch. Bimetallic strip consists of the two types of metal bonded together. That strip expand and contract at a different rate when heated or cooled. Expansion and a contraction make the coil tighten or loosen. This bimetallic strip is curled into the coil so it winds up or unwinds as the temperature changes, resulting in a tilting of the mercury switch at the top. When the temperature of the building is above or below the temperature that was set on the thermostat, the switch tilts in one direction and cause the mercury to touch two bare wires so to turn the switch on. This creates a closed circuit. It turns on the furnace or air conditioner. Thermal energy contributes into a global warming. The burning of fossil fuel results in a release of greenhouse gases, such as carbon dioxide, into atmosphere, contributing to global warming. Some refrigerants also damage ozone layer. Ozone layer is a layer of ozone gas in the upper atmosphere that helps to reduce the amount of ultraviolet radiation from sun that reaches the Earth's surface. Damage to the ozone layer contributes to increase in skin cancer caused by excess of ultraviolet radiation. Geothermal energy is the thermal energy of the earth. Geo means earth. If you look at the structure of the earth, taken from Wikipedia, inner core and outer core store enormous amount of thermal energy. The temperature at a 6,000 kilometers deep into the center of the earth can reach up to 6,000 degrees Celsius, and it decreases as we move closer to a lithosphere or crust of the earth. That kind of energy we have seen coming out through a volcanic eruption. Lava that comes out is very hot and burns everything in its way. Geothermal energy is the biggest energy after energy coming from sun. However, it is very little used. Geothermal energy is a thermal energy generated and stored in earth. The underground water temperature increases by 1 degree per 100-meter depth. However, in some places the temperature of the underground water is even higher as crust is thinner and is closer to the hotter layer of the earth. Those places are called geothermal places. We can use geothermal energy for generating energy or heating the homes and buildings or generate electricity. During the winter, the temperature below the ground is higher than the temperature above the ground. During the summer, the temperature below the ground is lower than temperature above the ground. The geothermal system is a system that transfers thermal energy from under the Earth's surface into the building to heat it during the winter, and transfer thermal energy from the building into the ground to cool the building during the summer. In a geothermal system, a liquid antifreeze water mixer is pumped through a network of plastic pipe that is placed meters underground. This system, after it's set up, can be very effective and long-term energy-saving system because it is very low maintenance system. This is a simple diagram illustrating geothermal heating and cooling system that is used to warm up or cool down the house. The geothermal energy from below the ground is transferred to the heating system inside of the building during the winter, heating the building because the temperature above the ground is much lower than temperature below the ground. So that thermal energy through the pipes is transferred in the building, releasing that thermal energy, warming up the house, and is sent back to the ground to pick up more thermal energy. During the summer, the thermal energy is reversed because the temperature is higher above the ground compared to temperature below the ground. So that thermal energy that is picked up by the water is sent down ground to cool down, to cool off. So that means that water, after is being fresh and cold, is circulating back to the house and picking up more energy, thermal energy, more by decreasing the temperature, and is sent back again, and that cycle continues until the house is at a comfortable level of the thermal energy. And that is it for this lesson. It's a short lesson. I hope you enjoy it, learn something about it, and have a good one.